All right, today we're going to be talking about radiation surfaces or radiation in real surfaces. Previously, we've been talking about black bodies, these surfaces that are not real. There's no real black body, maybe with the exception of the microwave background radiation that we talked about. But there's really no true black body surface. Every surface emits light as a function of the wavelength and as a function of direction. Not ideally, right? It's very, you're not ever going to have a surface that's perfectly ideal as a black body. So just to remind ourselves, when we're talking about a radiation problem, we're always talking about two things. We're talking about what's coming in to a surface, and then we're talking about what's leaving a surface. We always care about both of those components. And when it comes to radiation, the properties of the surface can affect the absorbed and the emitted part of it separately or differently, okay? So we're going to be talking about how the wavelength plays into this, and then I'll go a little bit further on the next slides, but this graphic here attempts to show you that, in fact, as a function of emitted angle, you could have different emitting properties. The surface can behave differently. So here we have some little differential element in the middle. It emits a ray at this angle theta and at this angle phi. And as a function of those two angles, the likelihood of emitting a ray can change. Right? You can have some emittance or emissivity that changes as a function of those angles. Okay, so let's go through some of the I guess, terminology or concepts related to real surfaces. And then I'll kind of show you some examples of how this is used. But today is mostly going to be going over that. And then hopefully at the end, we'll have time to talk a little bit about gray surface radiation exchange, which involves this concept called radiosity. I think some of you guys have probably heard before. Okay, so let's go through some definitions here of concepts. The first thing we're going to talk about, when we're talking about a real surface, we're talking usually about the emissivity of the surface. So let's define emissivity. Right, emissivity of the surface. Before we thought about emissivity, we say we have some rate equation, and it's sigma times epsilon, the emissivity times area times the temperature difference to the fourth. That emissivity that we've been assuming is a single constant usually, right? And now we're going to break this out where we're not assuming that emissivity is always a constant. It can be some function. So emissivity, just as a starting point, is what? It's the ratio of the emitted surface, of the radiation emitted by the surface, so the ratio of radiation emitted by a surface to that of the radiation emitted by a black body, black surface. Okay, so that definition probably makes sense. It's just how much power are you getting out per unit area, maybe per unit solid angle, divided by the equivalent that would be emitted from a black surface. So this value is always going to be between 0 and 1. Right? Your emissivity is always going to be between 0 and 1. Because you can't possibly emit more than a black surface, and you can't emit less than 0, right? So it's always going to be between 0 and 1, and it's practically never going to be 0 or 1, right? You're never going to have that. Like the blackest of the black surfaces you could ever find might be something like 99.999% absorptive, but they're never going to be 100%, right? So you're always going to be pretty strictly limited to between these two numbers. So emissivity is also, it's also a function of wavelength. It's a function of wavelength. And in fact, it can be a function of direction as well, like I said. So the second definition we have here is, we've got this concept of emissivity. So when we're talking specifically about an emissivity, we would be talking about a spectral, directional emissivity. Right, so spectral directional emissivity. Spectral meaning it's a function of wavelength. directional meaning it's a function of direction, right? It's a function of the angle that's emitted. So, you know, if we write that out, you might see it looks something like, okay, we have our epsilon. So epsilon at some wavelength lambda and at some angle theta phi. Right, so epsilon lambda theta phi is going to be our spectral directional emissivity. And that's just the ratio of our emitted radiation. Per area, per wavelength, and per solid angle. Right? Area, wavelength, and solid angle. So the units are, let me just finish this and divide that by the equivalent for a black body. Right? So it's emitted radiation for a black body in the same, right? So it's just the ratio of those two things. So let's see, the units in the numerator and denominator are the same, but the units here are going to be watts per meter squared, per area, per micron, per STRD. Okay. So STRD is a unit solid angle called steradian. Right? Steradian. So steradian is basically, you look at like the little, d theta, d phi here, this little gray rectangular square there. So that is kind of the solid angle associated with a given emitted ray. So that's going to be a normalizing factor here. So basically I'm saying if I took a little solid angle from anywhere in that hemisphere and an area of emission, that dA of the emitting surface, and a given wavelength, that's going to be the thing I care about in the numerator, and divide that by the equivalent for a black body. Okay, so the spectral directional emissivity, that's kind of the definition there. All right, so we have this little chart here. What I want to point out is it's often the case, I guess, that the emissivity can be a function of at least one of the two angles. Right? Usually it's a function of this theta, the angle away from the normal. It's almost never a function of phi. Right? It almost never depends on sort of where you're looking around like this. It's usually just up away from the angle. So if we were to plot this out, let's say we have, I don't know, a surface that at the normal has a emissivity of 1 or of 0.9. And so something like this, we're at 0.9. So what's going to happen is my angle gets closer and closer to the horizon. Typically, think about like you're driving in a car and you look off on the horizon and you see a reflection right on the road. What does that mean, or why is that happening? Well, it's because my reflectivity or my absorptivity is basically going to 0 as you get really close to the horizon. So absorptivity goes to 0, emissivity goes to 0. You get this high amount of reflection. So right at the horizon, I'm going to have something really close to 0. So when you plot this out, it might, let's see if I can draw this. It might look something like this. So you have this curve that kind of, that's very asymmetric, but okay, let's imagine it's symmetric. But you have this curve that kind of goes, the emissivity goes really close to 0 as you get close to the horizon, and then out away, normal angles away from the horizon, you get kind of this steady emissivity value, right? So normally that's just a function of this angle theta. So this would be theta on this axis. I guess this is, no, so this axis up here is theta, right? So this is theta. Okay. And it's almost never a function of phi. So we actually will never really talk about that phi, any phi dependence in this class. Okay, so we have this, talked enough about that. Let's talk about the next kind of version of this. We have spectral directional. It's a function of wavelength, and it's a function of direction. So we can kind of now start consolidating things that, like consolidating pieces of this to get sort of different versions of emissivity.